So my project is a good example of DSP and material science. So I'm doing a characterization of surface roughness of thin films using spectral analysis. Motivation, the PSD actually contains statistical information that is unbiased by the particular scan size and pixel resolution chosen by the researcher, whereas RMS doesn't. RMS is another way to characterize surface roughness. So I'm basically going to be taking the FFT of spatial height scans, 2D scans. So here's an example of what a crystal lattice might look like in space. You can see that there are planes of atoms, and here's a reciprocal space, the output of the DFT. G1 here is a vector that corresponds to, the length of it corresponds to 1 over D1, which is the spacing of the planes, and the direction is normal to the plane. So that's what you'd expect. Here's a very quick simulation. You can see here's a DC component, here's a point here and a point here that correspond to these planes, assuming it's infinite, right? And here's a stock image in Python. You can see that since this is mostly not periodic, most of the power is at DC, but there is a component here and component here that might correspond to the banister, railing, and post here. Moving on, niobium tinitride, widely unexplored superconductor. This AFM module is just some Python code that I wrote to read data from our AFM tool, which is atomic force microscopy. Here's 5 samples. Here's an example. Plus or minus 2 nanometer, 1 micron by micron. Typical scan for us. Here's a PSD with no windowing or filtering, also not scaled. You can see the DFT freaks out at the boundaries. So windowing allows us to smooth that out, makes the boundaries 0. DFT no longer freaks out. However, in this PSD, it looks better, but there's still this strong vertical line, and I'm actually arguing that that's an artifact of the scan routine. So the way the AFM works is it'll go down a row, come back, and go to the next row. Go down, come back, go to the next row, go down, come back. So this line, I'm arguing, is because this noise in the vertical direction is because of the discontinuity between rows. Because it doesn't exist in X frequency. It's only at 0X frequency, but it exists in all Y frequencies. And just to confirm, I took 2 different measurements, one at 0 degrees and one at 90 degrees, and that line rotates with the scan. So that makes sense. And here's a visual representation of a horizontal slice and a vertical slice, and you can clearly see the noise difference there at higher frequency. My attempt to filter it out, I tried a lot of different stuff. I'm sure there's a better filter out there, so I'm open to suggestions. But iteratively calling a Wiener filter seemed to help a lot, and in this Python implementation, the noise is estimated as the average of the local variance of the input. So here's what the output looks like. Visually, it's a lot better, although it filters everywhere, so there's still a bit of a difference between vertical and horizontal slices. You can see that here. However, the mean, unfiltered, is blue, filtered red. There is a bit of a difference in the mean. You can argue whether or not the mean actually means anything. Okay, scaling and radially averaging. This is actual useful information. It's going to take a while to calculate all this for the 5 different samples, but it's scaled according to the distance between pixels. Radially averaged to give this plot, which is the most useful. You can gather a lot of information from this, but I'm not going to go over it all. Mainly, you can see that there's an outlier, D2, which is a sample that was post-annealed at 1000 C for 10 minutes. And it is the outlier, is the highest temperature. The control would be room temperature, which is blue, which is down here. So that makes sense. Yeah. And here's a picture of D2, the actual surface of the sample. The roughness was so high, there was stress on that film, it started to delaminate. And here's some sources, and that's it.